We previously looked at simulating the outcome of a fair coin flip, that is a coin that lands heads with probability 50% and tails with probability 50%, using a set of realizations of a uniform 0-1 variable. So a uniform 0-1 variable was just a decimal value between 0 and 1, without any sort of bias towards being close to 0 or close to 1 or close to the middle, that it is just a decimal somewhere in that range. So if I asked for a realization of a uniform 0-1, maybe it's 0.37416. Maybe it's 0.8801239. Every time I do it, I'll get a different value. And what we wanted to do was to turn these decimals between 0 and 1 into the outcome heads or the outcome tails, such that it was random which one was assigned, but that if I was given a uniform point, I had a fixed rule to assign it. And so to do this, I needed to divide the, I suppose, slab of probability density where the uniform point could be selected from, such that half of the area was assigned to heads and half was assigned to tails. So we visualized it something like this. In this case, I said if the value lands less than or equal to 0.5, then I'll say the outcome's heads. If not, I'll say the outcome's tails. So I put a little 2 blue X's in the first case on the left. That's about, I don't know, 0.1, 0.15 maybe, so that would be called heads. The other one, more like 0.75, would be called tails. That's not the only rule I could assign. I could have split the area 50-50 in a different place. I could have called the first half tails and the second half heads. As long as I've got my rule, that's fine. We also saw how we could simulate outcomes which were not equally probable, like the simple one flip of a coin. So here I've got a binomial random variable with parameters 2 and 0.5. So I can still think of this as being based on coin flips, but in this case it's based on flipping 2 fair coins and counting, say, how many heads. So a quarter of the time I would get no heads, tails, tails. A quarter of the time I'd get 2 heads, on average, heads, heads, and half the time I would get 1 heads and 1 tails, either tails, heads, or heads, tails. So to set this rule up, I needed to assign a quarter of the outcomes to 0, on average, a quarter to 2, and 1/2 to 1. So dividing up the probability density like that, I've got, it's not a great drawing, I'm not sure the middle slice is half the area, but roughly speaking, if you'll pardon my bad artwork, that's roughly how I could make this work. So just formalizing some of that idea that we saw on the previous slide, because when I wanted to divide the areas into the proportions a quarter, a half, and a quarter, the actual rule which I worked on was said if it was less than a quarter, call it 0. And then if it was between a quarter and 3/4, call it 1, because I was sort of adding up that the width of each slice had to be added up, so I knew where the next, I suppose, barrier or cut point was. And this is the idea of a cumulative probability function. It doesn't say what's the probability of a given outcome, but it's saying if I choose a point, what's the chance that the result of the random variable is less than or equal to the point I'm looking at. So if I start with a simple regular fair 6-sided die, roll it once and call the outcome the number shown, Then the probability mass function, I hope, is fairly straightforward, that I have probability 1/6 of getting a 1, probability 1/6 of getting a 2, same for 3, 4, 5, and 6, and there is no possibility of any other outcome. So if the point I'm interested in, if I roll a die and say, what's the chance that the number shown is less than -7, or less than -3, or even less than a half, there is no possibility of that. No numbers on a die are less than any point I'm interested in if that point is less than 1. The chance of rolling the die and getting a result less than 2 is 1/6, because the only value I can get, which is less than 2, is 1, and that happens with probability 1/6. Similarly, the chance of a result less than 3 is the chance of a 1 or a 2, so that's 2 chances in 6, or 1/3, and so on. So if I actually work out where the cumulative probability jumps up here, it jumps up at every integer. If I'm interested in a point which is less than 1, then there is no chance that the die will show a number below my point. If I pick a value which is at least 1, but less than 2, 1.4, the chance I roll the die and get a value less than 1.4 is the chance I get a 1, which is 1/6. Similarly, if I pick a point which is at least 2 but less than 3, 2.9 for example, the chance I roll the die and get a number less than 2.9 is the chance I get a 1 or a 2, and that's 2/6 or 1/3, and so on. Keep adding these up at every integer, I jump up by 1/6, and at the very top, if I pick a point which is 6 or more, the chance that I roll the die and get a number less than 387 is certain. What I get if we plot this up looks a bit like this series of steps. Now, as I've drawn it, I have drawn the sort of the vertical connectors in here. Technically, it's discontinuous there, but I've just drawn this for visualization purposes, that's what it's doing. It flatlines below the smallest possible value at 0. It flatlines at above the largest possible value at 1, and it just steps up in between. Now, this might seem like an overcomplication of what we've already seen. We already knew how to simulate discrete outcomes, so why do we need to start plotting cumulative functions? Well, the full answer to that will actually come in the next section. We can use these cumulative probability functions to generate realizations from a discrete probability mass function. And the way that we do this, well, if I write it down, the rule looks quite complicated. What this says is, well, start with a uniform random number, ui, uniformly selected between 0 and 1. And if I want a realization xi of the variable x, then what I would do is I'd set my simulated xi to be the smallest value of k, such that the probability that x is less than or equal to k is bigger than my uniform point ui. Now, when I just sliced the block of probability density up and said, okay, the first half is heads, the second half is tails, I think that was quite intuitive that it was doing what it said. This, I think, much less so. But if I think about it, what this actually means is that if I draw a uniform point between 0 and 1, so that's like sort of throwing a dart up the vertical axis such that there's no bias as to where it lands, not towards 0 or towards 1 or towards the middle, it's equally likely to land anywhere between 0 and 1, then I can sort of read off the value on the horizontal axis. So if I take this same example, it came from rolling a die, and I draw a uniform point, 0.571. If I read off 0.571, then what this rule is saying, I can think of it as pick a point on the vertical axis, look across horizontally, and then read down where that horizontal line would strike. So here, that would be that xi is 4. So hopefully you can see that 1/6 of the points would strike the wall at 1, i.e. anything between 0 and 1/6, so 0 and 1.66 occurring. Anything that's between 1/6 and 1/3 would strike the wall at 2, and so on. So this seems like it might be an overcomplication, but it's a very useful building block towards continuous value simulation, as we will see soon.